I'm sorry I can't be there with you. I returned from Manchester yesterday.
Yes,
And
yes, we can hear you.
okay, great. And tomorrow I have an offsite with my research group. So it was just impossible to be there in person, but we'll try to make do with this. So I'd like to share with you some of the experiences I had as an accidental benchmarker. I started my career actually back in 1973, and that's a picture of me in my office at Argonne National Laboratory. That was taken when I was an undergraduate. I was selected to be an undergraduate, spend a semester with a scientist kind of deal at Argonne National Lab. And I had one of those life-changing experiences, changed the course of my career and what I actually ended up doing. So I began at that time working on a project called IcePack. IcePack was to design some software for solving eigenvalue problems. And the algorithms came from this book by Wilkinson Reich. It's called The Handbook for Linear Algebra. It presented a bunch of state-of-the-art algorithms for solving eigenvalue problems. And the task of IcePack was to translate those ALGOL programs into Fortran. So it was really a translation process. And in that translation, we were trying to develop software for the eigenvalue problem, but software that would be portable, that would be able to run on all of the computers that we had access to at that time. So computing was a little bit different than today. Today we have an IEEE standard for floating point. Back in those days, there was no IEEE standard. So running a program on a machine at that time, without a guarantee of the kind of numerics that was going on underlying, presented many challenges for developing software that was dependent on an iteration scheme that had some convergence criteria. So we were trying to develop portable programs in that context. So that was the IcePack project to do a translation of ALGOL programs into Fortran. If you know something about ALGOL stores things by rows. We did a very faithful translation and translated the ALGOL into Fortran, accessing elements by rows. If you know something about Fortran, it actually stores by columns, and that had a rather important impact on performance, a rather deadly effect on the performance of the software. So the software didn't perform very well, but we had developed algorithms that were in fact portable across machines at that time. There was also something else that was starting about that time called the level 1 BLAS. Level 1 BLAS did vector operations. That is, they did things like dot products or take a multiple of a vector and adding it to another vector. So these were to be standard routines that allowed manufacturers to do an implementation of them on their architectures, trying to exploit performance as best they possibly can. And then it was going to be our job in terms of developing software that was going to be in a position to use those linear algebra subprograms as building blocks for our linear algebra software that was to follow. It was about that time that I wrote my first research paper, and it was on unrolling loops in Fortran. This is something we take for granted today, but the idea of unrolling loops was really new at that time. So unrolling a loop basically allowed one to put multiple instances within one iteration of the loop. So if you unroll to a level of 4, as is described there for that AXB operation, taking a scalar multiple of a vector and adding it to another vector, we would be able to expose a number of things that would perhaps allow things to run efficiently in a pipelined fashion. So we were able to express things in a way which gave us some improvement on performance, given the architectures that we had available to us at that time. So we saw about a 15 to 20% improvement in performance by doing this unrolling technique. And it was something that I wrote up and actually formed the basis for the BLAS routines that were being created at that time. So the BLAS routines used this unrolling technique in their implementation to extract that 15 to 20% improvement in performance. And the original BLAS paper is this Tom's article that appeared by Chuck Lawson, Dick Hansen, David Kincaid, and Fred Crow, which described this interface, which became a building block for many of the linear algebra that followed. In fact, we used those BLAS routines in a package called LinPack. LinPack is a package of linear system solvers that were developed in the late in the 80s that sort of provided a portable basis for describing systems of equations, singular value decompositions, and least squares problems. And it was built on top of these level 1 BLAS operations. It was about that time I became an accidental benchmarker. In this user's guide for the LinPack package, I put together a test to look at the performance for solving a system of linear equations. And that linear equation was for a matrix of size 100. And I looked at it solving that problem using the software from the LinPack package. And I put together a little table in the appendix to the user's guide. And that appendix turned out to be the first benchmark for the LinPack benchmark software. So this is a table that appeared in the user's guide. It listed a bunch of machines, some 23 different machines, all solving a system of linear equations of size 100, listing them by the speed that or by the time it took to solve that problem. And the handwritten scribble there that you see is my conversion of the time to solve it into an execution rate. The system of equations, it took 2/3 n cubed floating point operations. It did Gaussian elimination with partial pivoting. And the fastest system was a machine at the National Center for Atmospheric Research in Boulder. And it solved that system in 14 megaflops. So that was the execution rate on that Cray 1 system back in 1977. That list of the performance grew as various manufacturers came to sell us their machines at Argonne. I would ask that they run this benchmark on their machine, and I would enter it into the table. And after a few years, I had a few hundred machines listed in this table for solving systems of linear equations using the LinPack software. So that was around 1978. I had a colleague at Mannheim, Hans Moyer, and his student Eric Strohmeyer. They had a list of the fastest computers that were ranked by the peak performance. And I had a benchmark that ranked machines by solving the system of equations. Hans said we should put together our lists and call it the top 500 based on actually solving a system of linear equations. So that was the origins of this top 500 list, which ranks the 500 fastest computers. It does that by solving a system of linear equations. The ground rules for this benchmark are that you have to use Gauss elimination with partial pivoting. That's the algorithm. You have to solve it, implement it on your architecture. You can use the best implementation, but you have to get an accuracy equivalent to doing the computation in 64-bit floating point arithmetic. So that was the benchmark. Solve that system of equations, make it as large as you possibly can. And we want to look at the asymptotic rate for solving that systems. So if you were to think of increasing the size of the problem, the rate of execution would increase until you got to until you reached an asymptotic point, and we wanted to capture that asymptotic point for this top 500 list. This list has been maintained since 1993. It's updated twice a year. It's updated at the Supercomputing Conference that's held in the States. This year it'll be held in Dallas, and it's also updated at a conference in Germany that's held in June. So the most recent results we have are for the June meeting of this year that was held in Hamburg. So this is a list of the number one machine. So think of this as the guy that performed the fastest from 1993. When we started the list, that was a thinking machine CM5. It was at Los Alamos National Laboratory, and it executed at that rate there of 60 gigaflops. So that was the rate of execution for solving that system of equations. And you can see how that's evolved over time. So the fastest machine today is from the Frontier system at Oak Ridge National Lab. It executed the benchmark at just a little bit over an exaflop. It had 7 million cores in the machine, so 7 million processes or cores were being used in this execution. The matrix was of size 24 million, and it consumed 21 megawatts of power during the execution of the benchmark. And if we look over the past 29 years, we see that the US has had 11 machines in the number one position. Japan has had 7, and China has had 3 machines. And I've also listed there the DOE machines that have obtained the number one position. So Oak Ridge has 4, Livermore has 3, Sandia has 2, as well as Los Alamos. Interestingly enough, Argonne has not had a number one machine, although they have had very fast high performance machines at Argonne National Laboratory. So that sort of is how the list is shaken out. Some of the highlights from this most recent list, the Oak Ridge machine is the number one, having been the first machine to exceed an exaflop. That one machine has, if we take a look at the top 500 computers and add up the performance of the 500 machines, the Frontier system is 25% of the sum of the 500 machines. So this list of the 500 machines is really top loaded with some very fast machines in the first 10 positions, and then a long tail of the rest of the machines that are there. The machine at Oak Ridge is capable of 6.8 exaflops when doing 16-bit floating point arithmetic. And I'll have a little bit more to say about that as we progress in this presentation. The top 10 machines, this time there are 3 new machines, the machine at Oak Ridge, a machine in Finland, and then another machine in France are new machines to enter the top 10 machines. The top 10 represents 52% of the whole performance of the top 500 list. So as I said, it's very top loaded with the top 10 machines having over half of the whole performance. Interesting enough, China is the top consumer of supercomputers. So it has the most supercomputers in China, and China also produces the most supercomputers. So companies like Lenovo, Inspur, and Sugan are the big companies in China that are making supercomputers that are sold around the world, but many of those machines are also being used in China. Intel, if we take a look at the top 500 machines, we see that Intel processors are used in 78% of those 500 machines, and AMD has another 19%. So that's rather striking. The x86 architecture, which is part of Intel as well as AMD, make up this 97% percent of the top 500 list are based on that x86 architecture. And this is a snapshot, if you will, of the top 500 list since it was started back in 1993. The red dots are giving us an indication of the fastest machine. We see that the fastest computer is at 1.1 exaflops today. The guy at the bottom of the list, the guy at position number 500, is at 1.65 petaflops. So roughly 3 orders of magnitude separate the number 1 and the number 500 system on the list today. If we add up the 500 machines, we get the blue dot. So the sum of the 500 machines is at 4.4 exaflops today. So you can see where things have been in the past. We get this inflection point around here in 2007. There's an inflection point here which changed the trajectory, if you will, of these curves. And a question might be, why did that happen? What's going on in 2007 that would change the trajectory? And I think there's a number of reasons for that. One reason is the end of Dongarra scaling. Dongarra scaling is this incredible situation that we had where we can make things smaller, put in the same amount of power and get a big increase in terms of the performance out of it. We also have Moore's law, which is slowing down. We also had a financial crisis around 2007, which may have delayed the replacement of supercomputers, resulting in sort of a slowdown in what we see in practice. And I think all of those things are probably true. If we take a look at this list and we look at my laptop, so I'm running here on a laptop which has a 4-core Intel processor. I can run the benchmark on my laptop, and when I do, I get 166 gigaflops. So that's really a stunning achievement, I think, for the technology. Having a machine that I mainly use to read email and occasionally give talks running at 166 gigaflops. If I take a look at the number one system, back in 1993 or 1994, my laptop is actually faster than those systems. Back in 1993, the fastest computer was a thinking machine CM5 with 1,000 processors at Los Alamos National Lab used for nuclear weapons design. So my laptop is faster than that computer, which is really an incredible achievement, I would say. This is a list of the number one machines. We reached a threshold of a teraflop back in 1997, and that was at Sandia National Lab in a machine called the ASCII Red. If we go ahead 11 years, we go through 3 orders of magnitude, reaching a petaflop, 10 to the 15 floating point operations per second. And that was at a machine at Los Alamos National Lab called the Roadrunner. And if we progress a bit further, after 14 years, we reached this exaflop rate, or 10 to the 18 floating point operations per second. I still have a hard time getting my hands around that amount of computing power. That's a billion floating point operations per second. That's just an incredible amount of computing power that we have today in our high performance computing. And we think about where we're going in the future. When we will get to the next 3 orders of magnitude increase. Will it be 14 years, or will it take longer to get to Zeta scale computing, or 10 to the 21 floating point operations? So that's a question I don't have an answer to, but it'd be interesting to see where the technology goes and what takes us there. So this is a list of the top 10 machines today. Again, the machine at Oak Ridge, the Frontier machine, is number 1. It's based on AMD parts. It has an AMD CPU and an AMD GPU. It uses a Cray interconnect called Slingshot. The total number of cores is 7.7 million. It ran at 1.1 exaflops, and that was 55% of the theoretical peak performance. So the theoretical peak is paper and pencil, comes about from a paper and pencil calculation looking at the cycle time, the number of operations you can complete per cycle, and that would and the number of processors, and that would give you the theoretical peak. And here we're achieving 55%, or a little bit over half of the potential peak performance for the machine. The 45% that we're not achieving is the result of parallel processing of data movement, overhead, and general overheads in our program. The power consumption is 21 megawatts. So think about a megawatt. So if you had a computer at your home, and you used, and it took 1 megawatt, and you used it for 1 year, you would get a bill from the electric company for $1 million. So a megawatt year is $1 million, roughly. And so the machine at Oak Ridge is about $21 million just to turn it on and use it for a 1 year period of time. Now that machine, the Frontier system, is about $600 million for just the hardware. And again, we have to pay for the power, of course. And the machine has an efficiency, or gigaflops per watt, of 52. So you want to have a machine which has the highest gigaflops per watt. And the Frontier system does in fact have that. And you could see the rest of the machines on the list. The Fugaku machine in Japan is number 2. It's based on an ARM processor that's been modified to use vector instructions. And they have an interconnect that was designed by Fujitsu, which has 7 million, little over 7 million cores in it. But it has no accelerator in the sense of a GPU-like accelerator. The parts that are highlighted in red are accelerators, and all of the top 10 machines, except for the Fujitsu, are based on some accelerator from AMD, NVIDIA, or some homegrown thing like the Sunway or the machine at the Tianhe 2A, which is a homegrown accelerator that was built by the Chinese. This is a look at how those top 500 machines spread out. So we're plotting here the performance of each of the 500 machines. You can see the number 1 machine there standing out quite a bit above all the other machines. And you can see that the top 10 machines really dominate this list here, and this very long tail of machines follow from that list. So perhaps it's unfortunate that we have, we list 500 machines. I think we can get away with listing the top 100 machines that are really being used for high performance scientific computing. Many of these other machines are not really in the scientific area. The other thing to note is where these machines are. So China has 173 machines, US has 128. Unfortunately, the way I've got this formatted, you can't see the US there. Japan, followed by, I think it's Germany, France, and so on down the list. But the striking thing is China has 173 machines, followed by the US with 128, and then the others come in with roughly 30 machines or less in their country being used for high performance scientific. So this benchmark that we have, the LINPACK benchmark, is something we've been using for a long time. It has a lot of positive features. It's pretty easy to understand. It's easy to describe. It's good for showing trends in the technology. However, a lot has changed since 1979. Back in 1979, computing arithmetic was very expensive. And today, our machines are really over-provisioned. And floating point arithmetic is not that expensive. The expensive part is in data movement. And the LINPACK benchmark really doesn't correlate with real applications and how they perform. LINPACK is based on dense matrix multiply. That's the computational kernel for the benchmark. And today our machines are really designed not to solve the kind of problems that are being run on the machines. So if we take a look at the workload for a typical DOE center, what's being done is trying to solve a large-scale partial differential equation in 3 dimensions. And they take that partial differential equation, discretize it, and what we end up solving in terms of solving that 3D problem is trying to solve a sparse matrix problem. So it's a linear system of equations again, but the matrix is not dense, it's sparse. And we use an iterative technique to solve that matrix. And we have to do that in parallel. So there's a lot of communication that takes place. It's not computationally intense as matrix multiply is. We have a sparse data structure that we're manipulating and doing operations with. And the results are quite different in terms of performance. So we have another benchmark called HPCG, which implements an iterative method, conjugate gradients. We're solving a system of equations with this benchmark. We have a large sparse matrix A, we have a right-hand side, and we're using this iterative technique to compute a solution X. And the implementation is done using conjugate gradients method. So it's a 27-point stencil that's being used as the computational problem. And there's an opportunity for doing some preconditioning, and there's a way to check the results as well. So this is the result of that benchmark, HPCG benchmark. Unfortunately, Frontier, they didn't have time to put together a run on Frontier, so we don't know how it performs, but the rankings here show that the Japanese machine, the Fugaku system, is the #1 machine, and it performed the benchmark. Here you could see 16 petaflops is the performance that they achieved for this benchmark for solving a large sparse matrix problem. By comparison, the HPL or the LINPACK number is given in that column. So you could see the difference between the LINPACK number and a more realistic problem. And when we look at the fraction of peak performance for solving this HPCG problem, we see that we're only achieving on the order of just a few percent. Here, the Fugaku system is actually doing a very good job of 3% of the theoretical peak, where many of the other machines are getting far less efficiency. We look at this machine in Finland, the #3 machine, and it's less than 1% of the theoretical peak. The machine in Finland is very similar to the machine in Oak Ridge, the Frontier system. So I would expect to see a number very similar for running the HPCG benchmark on the Frontier system, but we just don't have that number at this point. So if we take a look at plotting some things, so the theoretical peak is plotted here. That's the black dots. The HPL number, the LINPACK number, is the green dots, and the HPCG number, this iterative method for solving systems of equations, are the blue dots. So you see this gap between the performance of a dense matrix computation and a sparse matrix computation. The sparse matrix is more perhaps an indicator of what we would see on machine today solving realistic problems on those systems. So it really says we're not getting anywhere near the peak performance for these machines. Today the landscape for high performance computing is changing. We have machine learning and artificial intelligence that are creeping into our computations, and the vendors understand that they should provide us with hardware so that we can adequately solve those problems. The hardware for solving machine learning problems and deep neural networks, they don't need a lot of precision. So they can get by with much less precision. In fact, they can get by probably with 16-bit floating point arithmetic. They don't need 64-bit floating point arithmetic. So we see a lot of machines being produced with this less than 64-bit floating point arithmetic in it. And, the IEEE provides a standard for doing things like double precision. If we take a look at the representation, there's 11 bits in the exponent and 52 bits in the fraction. Single precision floating point arithmetic, there are 8 bits in the exponent and 23 bits in the fraction. And IEEE provides 16-bit floating point arithmetic, which only gives us 5 bits for the exponent and 10 bits for the precision or the fraction. So with 5 bits of exponent, it says the largest number you can represent is 65,000. So if you go above that, you overflow. So with 16-bit IEEE arithmetic, it's important that we keep numbers in a certain range, and it requires us to do a lot of scaling. Google said that they were going to build hardware that doesn't have IEEE 16-bit floating point. They designed their own floating point, which uses 8 bits to represent the exponent and 7 bits for the fraction. And that allows them to have a much larger exponent. In fact, it's the same as used in single precision 32-bit arithmetic. They just have less precision, 7 bits of precision. So it's interesting to see that some of the commercial search groups or people that are selling cycles are now designing their own hardware for doing floating point arithmetic. And that's a trend which I think is interesting to see. NVIDIA has yet another format which for doing floating point, which is sort of in some sense the best of both worlds for 32-bit arithmetic. They have 8 bits for the exponent and 10 bits for the fraction. This is a data format that's only used for the computation, not for storage. So they accumulate results in registers, in matrix registers, in fact. And then when they store the results back, they have to go through a truncation process to get it to fit into the data format in storage. And what we see is cloud vendors now doing their own processors. Google's has this TPU, which does this bfloat 16. Amazon has their Gravitons for doing their kind of computations. And, Apple now has designed their own processors. They have an M1 processor based on ARM technology. So these companies are not relying on Intel for their processors. They're making a decision to build their own. So they're actually designing and implementing their own processors. They're fabricated somewhere else, like Taiwan, and then providing them with their own processors for use, not relying on those commodity parts that we see from Intel or AMD for their solutions. And NVIDIA, with their newest line, Hopper, has even gone to shorter precision. They have a floating point 8 representation for doing operations. So they're going to operate where they have 5 bits for the exponent and 2 bits for keeping the fraction or the precision of the number in one of their formats. In another, they have 4 bits for the fraction and 3 bits to represent the precision of the number. And you could switch between those or use them in some way to carry out your computation. But they're getting by with 8-bit floating point arithmetic, which is the interesting thing. And some AI applications can effectively use that, or at least that's the theory. Okay, so there are many reasons for going to mixed precision. We should start thinking about them for our own applications. The primary reason is that by using mixed precision, we have less communication. So we have less data movement between the processor and memory. So if we're going to go to 16-bit floating point arithmetic, we end up with a factor of 4 in terms of communication. And today, communication is really the most expensive part. We also reduce the memory footprint. The arithmetic is faster, usually a factor of 2 by reducing it in half. So going from 64-bit to 32, we usually get a factor of 2. And going to 16-bit, we usually get another factor of 2. It could even be better in some cases. So we should be thinking about implementing our algorithms using some kind of mixed precision to look at effectively getting this kind of improvement in performance. So we have another benchmark that we've just rolled out. It's called HPL AI. Maybe that's a misnomer. We're thinking about changing its name to HPL Mixed Precision, and it will basically solve a system of linear equations, a dense matrix problem. It allows for the matrix to be represented in lower precision, 16-bit perhaps, doing the factorization, the LU factorization by Gaussian elimination. That's part of the rules in 16-bit floating point arithmetic. And then using that factorization as a preconditioner to an iterative method to actually solve the underlying problem, the dense matrix problem. So, this is a situation where we do a short precision factorization of the matrix, L and U. We end up with an approximation to the original problem that we're trying to solve. And we use that approximation as a preconditioner to an iterative method. We're going to use the iterative method on a dense problem. And that preconditioner is pretty good. We're only needing a few iterations with that lower precision preconditioner to allow GMRes to converge to a fully accurate 64-bit result. So we do a low precision order n cubed factorization using 16-bit. We get an approximate solution X, and then we use an iterative method with the preconditioner L and U to effectively solve our problem, where we can then get the results to the accuracy as if we had solved the original problem using 64-bit floating point arithmetic. So this is the results from that benchmark. So this was run on Frontier using 8 million cores, and they achieved an execution rate of 6.8 exaflops. So again, they factor the matrix in 16-bit arithmetic on the computer. They use that as a preconditioner to start GMRes in 64-bit arithmetic. GMRes is iterating, and it converges to the solution they would have gotten had they solved the whole problem in 64-bit. So that amounts to a 6.2 speed up in performance. You can see that going down the list, all of these computers are getting an effective boost by using this mixed precision technique to enhance the performance. So we should be thinking about how we can effectively use this mixed precision in our numerical computations. And if we go back to our plotting of the performances, the yellow dots represent the performance for the HPL AI benchmark. Again, getting quite a bit improvement over what we got in 64-bit arithmetic for that same problem. Okay, so I'm gonna conclude here. So the takeaway is the hardware is constantly changing, going from scalar to vector to distributed to accelerated to mixed precision perhaps. We've had 3 computer revolutions that have taken place. One is in high performance computing, driving scientific problem solving. We also have deep learning, and we have edge computing. I think Pete gave a talk the other day about edge-based computing. All of those have enhanced our ability to solve problems. The algorithms and software always follow the advances that are made in hardware. In fact, the way I think of this is the hardware designers build a piece of hardware that they can build, and they throw it over the fence, and we, meaning the applications people and the software people, have to now figure out how to craft our applications, our algorithms, and our software to effectively use that hardware. So in some sense, the hardware has tremendous capabilities, and we're faced with this job of improving on what we can do for that hardware. So as a riff on Feynman's lecture based on quantum effects, Feynman said there's plenty of room at the bottom. The riff here is a paper that was written this past couple years ago, I guess now, by Charles Lyserson and company that appeared in Science about there's plenty of room at the top where we have to use techniques of algorithms and software to extract more performance from our hardware designs. So I think I'll stop there, and I'd be happy to answer any questions that you might have in the remaining minutes.
Hey, Jack, this is John Malakrami.
Hey, John.
So I was wondering whether you think that we need a data movement and communication benchmark that's sort of separate from the HPCG calculation, something like maybe a batched matrix transpose, because, you know, rather than doing just say like a global transpose, the batched matrix transpose would have some locality in it, which is like, you know, common in computations, right? I was wondering whether you think that we need some sort of data movement benchmark or...
Yes, we definitely need more benchmarks to give us a better feel about the performance space for these machines. Matrix transpose kind of operation is a good idea. You know, the thing that comes to mind is looking at FFTs. There they have a lot of data movement associated with carrying out that computation, and looking at a benchmark that would effectively try to capture the kind of data movements you're talking about in that would be a good thing to do as well. But, you know, batched operations are certainly a good way of doing it. This batched operation is basically doing the same operation on independent sets of data in parallel, embarrassingly parallel, and looking at, as John mentioned, the performance that we would get out of that batching.
Mm-hmm. Thanks.
Hey, Jack, I got a quick question. So the SC21 that had happened, Tianhe 3 and the Ocean Light clusters, you know, they had these Chinese clusters, they had, I guess, disseminated some LINPACK benchmark information. And you just gave a presentation now in which, I guess this list was updated in June, but it failed to make the benchmark or the list there. Do you have any comments as to what the reason there for that might be? And also, do we understand like the technology that they're using for their microprocessors? Like, is that homegrown, and could we learn anything from that, or is that something that they're learning, you know, from our hardware development process here? And,
right,
and my one more question. The other question is, do we know what type of applications that they're targeting as well? And that's all.
Sure. So you're referring to two machines that have been designed and built in China. This has a long history. A number of years ago, the U.S. had embargoed the sale of Western technology to China. China was using Intel parts and other parts from the West to build their high-performance machines. And the U.S. was not in favor of that. So they basically embargoed Intel from selling parts to certain places in China. And the result in China was that Chinese invested more in terms of designing hardware and putting that in place. And what we see today are two machines that you mentioned, the Ocean Light and the Tianhe 3, which are based on Chinese processors, no Western processors. The processors were designed in China. They were probably fabricated in Taiwan. That's my conjecture. That's not anything that's been officially reported. And the Chinese have decided not to submit benchmark results to the top 500. They've written scientific papers. They've described the architecture in some detail. Those papers have been submitted. And last year, the paper that was submitted of performance that was run on the Ocean Light machine won the Gordon Bell Prize. So these are real machines that are in place being used to solve large scientific problems, very competitive in terms of how they operate and the performance they're able to achieve. There are rumors that they ran the benchmark, the LINPACK benchmark, on both machines and exceeded 1 exaflop, but they chose not to submit the results. My feeling, this is my personal feeling, is that because those chips were most likely designed, or most likely fabricated in Taiwan at TSMC, the Chinese are concerned that the US may take some action against TSMC or Taiwan and requesting Taiwan not to fabricate parts for China. And that would have a profound impact on the Chinese processors, the consumption of Chinese processors, if they were restricted. There is fabs in China, but they're not at the same level of fabrication in terms of the resolution size that they're capable of at TSMC. So, or at least for the moment, I'm sure that they can catch up at some point, but right now they're not at that same level. So I think it's a geopolitical issue as to why they haven't submitted results to the top 500 list. It relates to not wanting to agitate, let's say, the US government into taking further action that would prevent technology and part development going to mainland China. But I think both machines are real. I think both are effective for solving large-scale problems and are equal or better than some of the architectures we have at our national laboratories. And what kind of problems they're solving, when you ask that question to the Chinese, you end up with a list very similar to what we see that we're using our computers to solve problems. A lot of energy-related things, combustion, looking at the nuclear weapon design, looking at nuclear reactors, and so on. So there's a list very similar to what we have for our list of uses of high-performance computing.
Thank you for your answer.
Okay, I guess I'm next. Thanks for the talk, and congrats on the Turing Award.
Thank you.
I have a follow-up question, I guess, on interpreting the top 500. Because a Canada supercomputer is split in two, even though it has the same file system. And there's also, I wonder about national security supercomputers like USA or China. And you just mentioned not submitting benchmark results. So, we know that the number one isn't going to be a secret because the project is just too big. You can't hide it. But on the tail end that you mentioned, what are your feelings about the top 500 and maybe a few systems not being listed there? And how much does that happen, do you think? Or any other thoughts? Thanks.
Right. So we know about the Chinese not listing their machines, but it's my guess that there are agencies in the U.S. that have high performance systems which are very powerful, maybe even special architecture designed machines being used by those agencies, and they tend not to care about or want to list the performance of their machines in a benchmark like the LINPACK benchmark or the top 500. So I think there are a number of machines like that. I don't think it's a large number. I think it's a small number, but I think there are machines out there which in the U.S. And maybe other countries as well, which have chosen not to submit results to the benchmark. And that certainly distorts things in a certain sense, but it's almost inevitable. We can't force people to submit results. We rely on them wanting to submit and to advertise the fact that they have a high performance system in their area.
Do you think that would be like top 30 or top 300, roughly, maybe? Guess?
So it's hard to predict. It's hard to predict. I guess that's the right way to say it. We do allow machines to be listed to submit results, but we do allow those machines to appear without listing where they're located. So if you take a look at the top 500 list, you'll see machines that have the notation classified, but they don't give a specific site where they sit. And some of those machines, I guess, are at those secret locations in the U.S. and other places. And there are companies that don't want to disclose that they're using high performance systems or the kind of systems that they're using. If you take a look at the top 500 list and look at where they're being used, industry has about 50% of the machines on the top 500 list. So, industry gets it that these machines provide some kind of competitive advantage for them. And, they're willing to invest in high performance machines. And, maybe some of those companies chose not to submit results to the top 500 because they don't want to give away the fact that they have powerful supercomputers in their backyard. But, the other thing I want to stress here is the top 500 list gives this long tail of machines which have some performance level which allows them to appear in this list. But there's only the machines at the top end are the machines that I would really call the real supercomputers in some sense. That top 10 list is really where most of the power for supercomputing sits.
Okay, thanks.
Thank you for spending your time with us this evening. You had focused a lot on mixed precision arithmetic and how that inertia in that space around current hardware, especially around the AI and ML communities, is influencing directions of where we might be thinking to get more performance out of our systems. However, people outside of AI ML perhaps are not as willing maybe to adopt that usage of lower precision for various reasons, just perhaps even feasible. I'm curious what your thoughts are in terms of alternative number representation formats like posits, for example, that might provide similar opportunities to expand, allow for sufficient accuracy of representation in range, but with reduced number of bits, but nonetheless still have the difficulty of not having hardware that's adapted to that type of representation format. Do we need to be pursuing research that allows for and development of hardware that could accommodate different number of representation formats that could support communities outside of AML?
Yeah, I think that's exactly right. So I think we need to have research done to understand how far we can push things and in which direction we can push things. So, trying to explore the space in which applications can effectively get by with using lower precision and still maintain the fidelity that they need for their application. I mentioned one technique, maybe trick, coming from linear algebra, which allows one to use an approximation and then iterate to come up with refine the solution, basically, to get to the point where you would have gotten had you done the whole thing in 64-bit arithmetic. So, those are tricks or techniques that I think can be applied in different places and different areas to extend this. And, using posits. So, my friend John Gustafson is the guy who invented this. This is a way to represent numbers different than the IEEE floating point arithmetic. That's an interesting research area, and it should be looked at very carefully to see if there's something there that should be effectively implemented in hardware. So I know of no vendor that's actually implemented posits in the hardware to allow it to really be tested at, compared to, what we get out of our commodity processors with the performance that we have. The thing I want to stress, though, is most of our machines are based on commodity processors. And, we as a scientific community might want to do some research into designing our own processors. The key word here is co-design. And, we talk a story about co-design where the hardware guys and the algorithm guys and the software guys get together to make decisions about how things are done. But in reality, the hardware guys just throw something over the fence, and the algorithms, the application and the software people have to scramble to figure out how to use it. We really need a situation where we can design a piece of hardware from the ground up and try to design it to do scientific problems. The closest example to that is the machine in Japan. So the Fugaku system was designed by scientists trying to understand what's needed to do the operations very effectively. And I think they come up with a good design. The ARM-based system they have using vector instructions is easier to program. It provides a basis which gets fairly high performance and allows scientists to develop their applications more rapidly than I would say if we had to write things based on, the model that we have today, based on a commodity processor with an accelerator, and trying to figure out how to pass data between those two parts of the machine to effectively extract the performance. That's a non-trivial thing to do. And the Japanese with the Fugaku system don't have that issue to overcome.
Thank you.
Jumping as a follow-up on that question, would you anticipate that FPGAs would actually come into form as a desired way to actually bring more flexible accelerators into the HPC space?
Right. So FPGAs, have a lot of promise, I would say, allowing one to program the hardware so it conforms to, whatever we need. So FPGAs have this ability, so we can program the kind of precision we want to get out of that hardware and do things that way. But I would say that the obstacle to overcome with FPGAs is how we do the programming. It's a different programming paradigm. It's almost like programming in 3 dimensions in some sense. Getting that right is really quite difficult. I find it hard enough to think about programming in parallel, and now we've got this other dimension that we have to deal with. And, we really haven't come up with, I'll call adequate solutions to ease the job of programming that kind of architecture. So it comes down to a matter of ease of programming the hardware. In the end, the most important resource that we have to optimize is our time. It's not the hardware's time, it's our time in developing these things. And we want to have something which allows the flexibility to do implementations rapidly and to get fairly high performance in doing that. And that becomes the point that we're trying to achieve. And I think FPGAs today are not at the point to optimize for that.
Gotcha. Thank you.
Hello. Next question, I guess, is if you have any advice for students or young people just starting their career.
Yes. So how? What's the advice I would give? Work hard is one thing. So what it comes down to is understanding the basics. So I started out. My career was very random in some sense. I had no plan to do what I'm doing today. Everything was a matter of a serendipitous kind of running around, finding things of interest and running with ideas, trying to be ahead of everybody else in terms of the ideas and the implementations to carry those out. Having a good basis in mathematics is important. Being able to understand how to do computer science correctly is also quite important if you're going to pursue a computational science career. So I would say those are two very important things. The mathematics, I would say, is the more important of those, and then try to understand how to do the computer science to allow you to do that. So I teach a course and it's in computational science for engineers. And I ask people on the first day, do you know how to program? And everybody, of course, says, yes, they know how to program. But then you start pushing and say, what do you know about data structures? What do you know about recursion? What do you know about other things? And they some of them, have no real depth in those areas. And those are fundamental issues that we should learn in computer science that really have a tremendous benefit in terms of our implementation. So understanding the fundamentals of the mathematics and of computer science go a long way in getting us to a place where we can build on that. So if I was going to give a recommendation for young scientists looking at doing a career in computational science, I would say a focus on math and computer science and try to understand how you could effectively apply those on the hardware that we have at the moment.
Okay, thanks a lot.
Any more questions? Yes, one more.
Nice. So there's been some discussion regarding Fortran in this group.
I knew that was going to come back.
Yeah. Okay. So I guess what are your thoughts on Fortran now and I guess going forwards?
Well, Fortran, so I learned Fortran as my first programming language. Today we use C++, but, I have a certain soft spot in my heart for Fortran. The Fortran standard has evolved, and it really looks nothing like the Fortran I knew as I was learning how to program in the early days. So I would say, Fortran's a fine way to do it. But most of the scientific computing is done through C++ today. So if I was going to make a recommendation, I would say, learn C++, do the implementation there. I also, am in favor of things like MATLAB, Julia, NumPy. So these are all good tools to have at your disposal to do the implementation. There are programs, that are written today, in Fortran, and they have to be maintained, and that'll be true going forward. But if you're gonna develop a new project, I would say you probably want to do it in C++.
Hey, I kind of have a question from a system architecture design perspective. So you mentioned that we're moving towards like mixed precision. That actually is kind of interesting because that effectively doubles the amount of data you can store. Like if you're storing it in 32 versus 64. I also feel like that's going to put a lot more pressure on the memory bandwidth. Like compute is cheap. So do you feel like in the coming decades that new systems are going to have like different architectures? Or are we just going to stick with fat node and hopefully a doubling of the network performance?
So, we take a look at the architectures that are being designed today, and they're putting the memory much closer to the processor. So, on the machine that we have, the memory is soldered into the GPU. So, it has a very tight coupling into it. The bus there is not that much of a problem. And, we have stacked memory today. So we have very fast stacked memory, which then goes onto the chip, and we can get fairly good bandwidth as a result of that. But, there are other architectures that perhaps more research needs to be done on to see how effective they can be used for scientific applications. And, the one that comes to mind is processor and memory. So we have, we think of memory as being the plane, and we're going to throw processors into the memory. So we want the data to be as close to the processor as possible to carry out the computations, and then communication networks running off of that. So bandwidth is critical. Latency is another thing which is going to come into the discussion. Both of those things are important. Today it's really about communication. Communication is the most expensive thing on our machines, and requires a fair amount of energy to move data as well. So that's driving up the cost in terms of the power consumption that we have. So if you can minimize all of those things, you would be in a better position. We always look at trying to develop algorithms which minimize the amount of communication. We try to prove that this algorithm has the minimum amount of communication. You can't do any better than that for this kind of an algorithm. And that's an area that needs to be explored a little bit deeper as well.
All right, thank you.